Welcome back to the deep dive. Today we're tackling something huge, a challenge that crops up everywhere, drug discovery, logistics, you name it. How do you find the absolute best solution when there are just, well, trillions of options?
It's a massive problem.
Exactly. So, our mission today, unpack how quantum bits or qubits and this really mind-bending idea called superposition, how they offer a revolutionary shortcut.
hmm
Get this. What if I told you there's a way to calculate all possible solutions to a problem, kind of at the same time?
That's the essence of it. See, unlike a classical computer bit, which is strictly 0, 1 qubits or different, they're tiny quantum systems.
Yeah.
We use their properties, maybe electron spin, maybe energy levels, to hold information.
Okay.
So a low energy state could be R0 and a high energy state is R1. And yeah, you string them together like 0, 0, 1 or 0, 11, making binary sets. That part feels familiar.
Right, but what really makes a qubit different from my laptop's bits, besides being tiny? Where's the quantum magic?
Ah, the magic is superposition. It comes from quantum mechanics. Tiny particles can sometimes act like waves. There's a mathematical description, a wave function, which basically outlines all the potential states they could be in.
Potential states. Okay.
So when we put a qubit into superposition, it's not just 0 or 1. It exists as both state 0 and state 1 simultaneously.
Both at the same time.
Yeah, roughly a 50% probability for each until we actually measure it, until we look.
That is wild. So, okay, if one qubit can be 0 and 1 at the same time, what happens if you have a few of them, all in that dual state?
That's where the real power kicks in. If you have a set of qubits and they're all in superposition,
Yeah.
they don't just add up. They represent all possible binary numbers for that set size all at once.
All of them.
Yeah. So say 3 qubits in superposition. They're simultaneously representing all 8 binary numbers, 0 through 7.
Wow. That's not just math, that's physically happening.
It is. It's a real physical state. We call it quantum parallelism. It lets us explore all those possibilities instantly.
How do you get them into that state?
We have to manipulate the qubit very precisely, often using focused energy, like laser beams or microwave pulses.
Okay, so quantum parallelism lets you explore everything at once. What's the practical upshot? Why is this so useful for us?
Optimization. That's really the core benefit right now. Think about finding the perfect molecule for a new drug,
Right, countless combinations.
or the most efficient route for a whole fleet of delivery trucks, instead of testing options one by one, which could take, forever. A quantum computer, using qubits in superposition, looks at the entire landscape of solutions simultaneously.
So like if you had 5 chemical parameters to optimize.
You might use just 3 qubits, maybe more, depending on complexity, but those qubits in superposition could evaluate combinations representing those parameters all at once. It speeds things up dramatically.
It sounds incredibly powerful, but maybe incredibly complex to control. How do you actually do calculations on these values that exist simultaneously?
We use gates.
But for quantum states.
Exactly. They're designed to manipulate these quantum states. For instance, there's one called the Hadamard gate. That's the one that basically puts a qubit into superposition, gives it that quantum nudge.
Okay, it gets into the both state. What else?
Then there's the CNOT gate. This one's really interesting. It creates entanglement.
Ah, entanglement.
Okay.
Linking qubits.
Right, linking them so one influences another. Like a control qubit can flip the state of a target qubit, creates dependencies.
Okay.
And you might have a comparison gate to check how close a qubit's value, or a set of them, is to some target you want. These gates let us perform mathematical operations.
So you apply these gates, but if everything is 0 and 1 until you look, how do you get a single clear answer out? Doesn't looking just collapse it?
Precisely. That's exactly what happens. When we measure the qubits after the gates have done their work, their wave function collapses. They snap into one definite state, either 0 or 1.
Like that spinning coin analogy, heads and tails at once, until you slap it down.
That's a good way to think about it. It lands on one side. So to find the optimal solution in our problem, we run the whole circuit, the whole sequence of gates, many, many times.
And the answer that shows up most often, that's likely the best one.
Statistically, yes. The most frequent result points towards the optimal solution. And we don't just run it randomly, we guide the system.
How do you guide it?
Well, entanglement helps linking qubits that represent related parameters make sure only valid or sensible combinations are more likely to appear. Plus, we encode system rules and constraints directly into the quantum circuit itself. Using specific gate sequences, we kind of sculpt the probabilities, pushing the outcome towards better solutions. Classical computers can sometimes assist too.
Okay, let's try to visualize this. Super simple example. Adding binary 1 plus binary 1. That's a 001 plus 001 in binary.
Perfect, yeah. We start by initializing, say, 3 qubits to the state 001, representing the number 1. Then we apply the quantum gates, maybe some CNUTs and others, that are designed to perform binary addition. The key is the qubits evolve according to those gates in superposition. We don't measure anything in the middle.
Right, no peaking. The whole calculation happens quantumly.
Exactly. Then at the very end, we measure. And for 001 plus 001, the state 010, which is binary for 2, will be the result that appears with very high probability.
So the calculation happens inside the circuit, and you just read the final answer. That's the revolutionary part.
That's the power.
This ability to tackle these incredibly complex problems, exploring countless solutions in parallel and guiding them, it's a fundamental shift.
It really is. And, understanding this is step one, applying it effectively. But we're really just at the beginning of this journey. The possibilities are just vast.
It really makes you think, doesn't
Yeah.
it? Imagine how much faster we could make scientific discoveries or completely transform industries if complex problems could be solved, well, almost in parallel, at speeds we're only now starting to grasp.